So, we are in this module 1 and I would like to place emphasis on one of the important issue that governs materials chemistry, that is the philosophy of synthesis, which is a inseparable issue as far as those working on materials. So, I call this as a philosophy of synthesis, the basis for chemistry of solids. Before I go into the details of other slides, I wish to record the contributions from Gausin and his group. Especially I have taken most of the resource materials from his group website. Therefore, I would like to place my acknowledgement for the resource material that I have taken from his group. When we come to solid state materials chemistry, we are mainly concerned about a few issues. Number 1, as I pointed out in the inaugural lecture, synthesis of solids plays a very important role, and if we need to have an idea of the synthetic strategy, the most fundamental understanding that we require is that of structure of solids. So, once you know the structure, you can design what sort of chemical approach that you need to take to synthesize these materials, and once you have a hands on grip on the structure and the way you need to make this material, it is possible to correlate that to the property of solids. So, structure and property together would help us in deciding what sort of functional application that we are looking for, and one of the main contributing factors to the chemistry of solids is the electronic properties of solids. The key developments in solid state materials chemistry is to do with synthesis and second structure and the properties, and one of the things that really holds this whole study of solids together is the function of defects. In solids, defect chemistry plays a very important role, whether we have to accept it reluctantly or so, the function of defects do play an important role. So, in combination with the defects in solids, the properties and structure will determine what sort of utility that we can think of. So, utility of solid state materials in advanced technologies can be realized if one knows how to synthesize a particular structure of a solid, and if you are able to fine tune the properties with the help of the intrinsic defects in the solids. In the next cartoon, I just want to tell you that fundamental understandings of materials chemistry has to do with knowing the different classes of compounds, and not only knowing the basics of the structure, but one can also come across several new phases which are serendipities in the materials chemistry field, and once we stumble at new ideas and new molecules or new solids, then we can actually translate that into applications. For example, this is application of a magnetically levitated train which has come from the basic understanding of superconducting solids, which were not existent. These are not available in nature, but then you, by knowing the structure and property, you can make these materials. And another group of compounds are these organic materials or organic molecules which are solids, which can be translated into display materials. So, as far as these sort of functional applications are concerned, one can start with the basic understanding of structures in solids, or by stumbling at some new phases, new solids, you can actually translate that to device applications. Now, when we think about material synthesis, first we need to understand making materials is a big world, and the group of people who are engaged in making solids are a host of groups who involve in a variety of solid state materials chemistry synthesis. Now here I have listed some of the portfolio of these synthetic methods, and purposely I have grouped them into some categories. One of the main and the most simplest approach to solid state synthesis is the direct reaction of solids, which is not very intricate. It does not call for very stringent application, but then once you get a feel for it, it is easier for to make many materials. Therefore, these are grouped under one: direct reaction of solids, precursor methods, or wet combustion synthesis. By this you can actually try to make solids in bulk. And another group of compounds that you can make is through vapor transport synthesis, which is not a very rigorously a solid state method, but then it is another approach by which you can actually aim for synthesis, purification, crystal growth and doping. Then you stumble at variety of wet chemistry routes, which we call it as soft chemistry, or as French people call it as chimie douce. These are soft chemical approaches by which without making much modification you can bring in a variety of new properties into a existing solid, and these are called as novel metastable phases, which you can realize using soft chemistry routes. And this also involves intercalation, and we can also try to synthesize material using electrochemical techniques, which is not a very hard protocol. So therefore this can also be considered as a soft chemistry route, and again ion exchange methods are also soft chemistry approaches. So here we are talking about direct solid solid interactions, and then we can also think of using wet chemistry routes to prepare solids, and there are other host of methods that are available, and this list is ever growing. For example, sol gel synthesis, aerogels for composites. Then again in the last decade we have witnessed many reactions based on nanomaterials for controlled size, shape and orientation, and then you have templated synthesis for zeolites, mesoporous materials, colloidal crystals and so on. And we can also aim for electrochemical synthesis, oxidation, reduction and polymerization methods. All these are grouped under wet chemical routes, and each synthetic approach distinguishes itself in stabilizing a particular phase or a group of solids that we are looking for. And another popular route for making solids, which often the physics principles are involved, therefore physicists often work on these methods. These are based on thin films using either chemical methods or physical methods, and then the most popular one now is the self assembling monolayers, which we call it as SAM, for making solids. And of course the most traditional way of making solids in the earlier decades is the single crystal growth for making high pure solids, and also one can use high pressure synthesis for making solids using either a dry approach or wet approach. So there are different ways in which we can make this solid state materials, and we will take some time in the subsequent lectures to see how these solids can be made using different functional groups, functional approaches. The heart of materials is how does one think about the chemical synthesis, the mode of formation and reactivity of new and existing materials which target specific relations between structure, property, function and utility. So therefore this forms the core of the materials chemistry approach. Now to name a few, I just want to bring in this candid illustration of yttrium, barium, copper. This is the most highly studied superconducting phase. This is a defect perovskite, and all you can see here is that X what we see here is what is controlling the superconducting property here, and this is based on in other words this X will control the copper oxidation state between 2 and 3, and that will make either the material superconducting or it will make it metal or semiconducting. So this is one of the group of oxides which really stands as a explicit example to show how chemical synthesis is a very vital protocol in realizing applications of many of the solids. Now by carefully maintaining the synthetic route, we can control the phase purity and we can realize these high TC superconductors which actually can be used for the applications like this. And there is another group of compound which is again a perovskite, and this is also a defect induced perovskite, and here again the X factor plays a very important role, and this X will control in this case not copper but here manganese between 3 and 4 oxidation state, which actually determines the oxide ion conductivity or the solid oxide fuel cell or the colossal magnetoresistivity. This is another very interesting compound where the chemical synthesis has really been established to control different properties as far as the applications are concerned. Another group of compounds which are layered cobalt oxide where you create a van der Waals gap, and lithium can be intercalated in this layers. As a result you can control the lithium ion conductivity and you can also look at the solid state battery applications. So these are a class of compounds where the chemical synthesis has been laid a lot of emphasis because of their functional importance. Now when we think of the philosophy of solid state material synthesis, choosing a method is very important. The solid state material synthesis methods are distinct to solution phase preparative techniques in the way that one devises an approach to a particular product and the way one chooses precursors and how they react in the solid state. So there is a basic difference between the synthetic approach for making solid state materials compared to solution phase preparative techniques. The form, the size, shape, orientation, organization and dimensionality as well as bulk and surface composition and structure of a material are often of prime importance. Also the stability of the material under reaction conditions, that is temperature, pressure and atmosphere, is a key consideration for making this solid state materials. Therefore the factors that influence solid state reactions are many, and this can be governed during the synthesis. The classes of solid state synthetic methods are of important, and other things that control the material synthesis is the size, shape and surface control of solids. For example, the solid state synthesis, choosing the precursor, choosing a method, designing specific structure property, all this governs the solid state material synthesis. Now when we think of the synthesis, we always think it is very easy because it does not involve much of wet chemical route. Therefore we often think solid state chemistry synthesis is often a very simple phenomena, but what we see is it looks deceptively simple, but when you actually go through the protocol you will find that it is extremely important to have a hands on experience on solid state chemistry. For example, you take graphite, which is a semi metal, and if you start doping potassium, actually this is a intercalation that is happening, and you try to pump in the potassium as a gaseous molecule, and when they arrive between the graphitic sheets, this is what happens. The potassium ions get intercalated between the graphitic sheets, and what happens in the first stage, selectively they occupy at random, and then as you keep on increasing the concentration of the potassium ions, you would see they go from room temperature metal all the way up to low temperature superconductors. Now how much of potassium that you control determines what sort of property that you are looking for. So, it is a simple graphitic semi metal, but the way you progressively go on doping potassium determines whether the material can transcend to a normal metal or to a superconductor. So, this is very important to understand that solid state principles are looking easier, but they are more involved. For example, if you look at the same reaction more carefully in a mechanistic way, you would see that initially the potassium is sent as a gaseous phase and they get absorbed, and during absorption there is a electron transfer, and after the electron transfer the potassium ions gets absorbed, and then there is a migration insertion of this potassium ions which are absorbed on the surface into the graphitic sheets. There and then because of this lot of other things can happen. Electron repulsion between the sheets can come because you are trying to accommodate a potassium ion between the graphitic sheets. As a result, your graphitic layers get deformed. So, several things happen here. For example, surface adsorption, sometimes this waxy top layer can actually sort of hinder the whole process. But if you selectively do the adsorption, then that transforms to electron transfer from potassium to pi star empty band of graphite, and then electron repulsion between interlayer leading to expansion of the graphitic layers, higher mobility of the smaller K plus compared to K0 will also alter the graphitic sheet alignment, and then this facilitates K plus ion injection into the layer space. So many mechanisms happen in a simple reaction between a gas phase gas solid interface, and therefore the mechanism of any solid state chemistry synthesis is quite involved. Now, in this intercalation chemistry between the sheets, this nice example of a solid vapor reaction, if we sum up all the mechanism that is happening, you can see it is not just one or two. There are more than 10 reactions that are happening in a simple solid vapor reaction. For example, the most important ones which can affect the property of graphitic stuff is the gas distribution. As a result, you can see the layer bending and elastic deformation of the defect induced graphitic layers, and then it transforms the whole material from a metal to a superconducting transition. So, how and why do solids react? What is the fundamental understanding about the reactivity of solids? Now, when we probe into these reasons, one of the things that we need to understand is when we look at solid state chemistry synthesis, the chemical reactivity of the solid state material is very important, and this depends on the physical dimensions as well as the bulk and surface structure and imperfections of reactants and products. All this decides whether such a chemical synthesis can be achieved with precision. Therefore, the individual reactivity of the reactants play an important role, and second, the factors governing solid state reactivity underpins concepts and methods for the synthesis of new solid state materials. So, once you know the individual reactivity of these reactants, then you need to know what sort of synthetic approach that you need to take in order to get this new materials. And solid state synthesis, making materials with desired size and shape, bulk and surface composition, and desired relation between structure, properties, function and utility, is distinct, and this is certainly quite different from the liquid and gas phase homogeneous reactions. So, what we need to understand is the chemical reactivity, and the factors governing such reactivity underplays a very important role in the synthesis. Again, when we talk about the reactivity, now we need to think about conventional liquid and gas phase reaction. Usually they are driven by intrinsic reactivity such as chemical potential, activation energy, temperature and concentration of the chemical species, whereas in contrast to that is the solid phase reactions, and in solid phase reactions we are talking about the chemical constituents, and we are talking about the crystal imperfections and the diffusion rather than intrinsic reactivity of the constituents. So, solid state reactivity is also determined by the particle size, shape, surface area, grain packing, surface crystallographic plane and so on. So, all these underlie the reactivity of solids. Now, we can actually classify what sort of solid state reactions happen or the reactivity of solids and how the chemical synthesis progresses. There are different ways we can realize this synthesis. First of all, we can think of a solid converting to a solid. This is one of the ways of realizing a solid state material, and the simplest example is that of a decomposition reaction. It could be a simple decomposition, conversion of say calcium carbonate to calcium oxide, which is a solid to solid product conversion, or it could be a polymerization reaction, or it could be a phase transition reaction. One of the classic example of this sort is taking molybdenum trioxide, which is usually a dihydrate, and if you heat this it transforms to a monohydrate and then it goes through a topotactic reaction to give MoO3, and this beauty here is it is a topotactic reaction involving water loss, and this can be actually monitored based on Avrami kinetics, and we can talk here about the single solid phase interaction where induction, nucleation, growth, product and depletion of reaction can be studied at one stretch. For example, if you take this example of unique 2-dimensional layered MoO3, you can see there are chains of corner sharing octahedral building blocks, and they are shared by edges with two similar chains. These are the corner shared ones which are edge shared here, and they make two similar chains like this, and this set of arrangement makes a layer wherein you can actually bring about intercalation between these MoO3 layers, and one of the example is that of introducing tungsten ion into this lattices, and once this MoO3 layers are stacked, then they create a interlayer van der Waals space wherein intercalation and deintercalation can be achieved. In general, the solid to solid transformations can be studied by Avrami kinetics. So, the nucleation and growth of one solid phase within the other can be described by this kinetics, where random and isolated nucleation at high energy defect sites with 1-dimensional, 2-dimensional or 3-dimensional growth can be studied. Expression for Avrami kinetics is based on this expression, where the fraction of the reaction that is completed is equated to this term, exponential term, that is 1 minus e to the power k t minus tau whole power n, where tau is the incubation time for nucleation and n is the dimensionality dependent exponent and k is your rate constant. So, in the initial phase you will see that the conversion is very slow, so which we call it as incubation, which is determined by tau, and then there is a phase where the growth of this solid state phase is occurring, which is in this plateau, and then once the reaction is complete it goes through a depletion time. So, this can be equated to the Avrami kinetics, and in solid state synthesis one can effectively study the kinetics kinetic parameters, and the growth can be monitored. If you look at a gas solid reaction, then we can study how a gas is getting absorbed. For example, if we have solid and we allow gas to come and get absorbed, now we can have many sort of reaction happening like this. Examples are oxidation reactions, reduction reactions, nitridation and intercalation. All these reactions can happen on a static solid phase and gas is getting absorbed, either it can diffuse or it can replace. So many things can happen. For example, we can passivate a metallic layer or a oxide layer using nitrogen. So nitrogen gas can get absorbed and something like this can happen. As you keep on adding or passing gas, you can see the surface is getting modified and the growth can proceed systematically to completely convert the solid phase with the gas that you are passing. So rate limiting diffusion of reactants through product layer growing on solid reactant phase can be achieved using this sort of solid gas reaction. And we can also classify the solid state reaction based on other examples. For example, in this case again absorbing H2S on silver to form silver sulphide is a solid state reaction, or passivation of aluminum by oxygen giving aluminum oxide is another solid state reaction involving surface and gaseous reactant. We can also look at the conversion of benzene to cyclohexane as one of the heterogeneous catalyzed reaction where hydrogen is adsorbed onto platinum and then it reacts with benzene to give C6H12, or there could be chemical vapor deposition where you can take gallium arsenide and you can pump in this gaseous reactants to form gallium arsenide indium phosphide semiconductors. So key surface species and surface reactivity where adsorption, desorption, dissociation and diffusion process are achieved, and by this way you can get new phases. There are other solid state reactions wherein solid plus solid can give solid products. Some of the examples are addition reaction. In this addition reaction you have zinc oxide and Fe2O3 forming zinc ferrite. In other words, this is a spinel compound. So this is a solid reaction yielding another solid, or you can go for a metathesis or a exchange reaction where you take zinc sulphide and treat it with cadmium oxide, you can actually get cadmium sulphide and zinc oxide. So this is a metathesis reaction, or you can go for alloying where you take zinc selenide and you add cadmium selenide, then you can get a solid solution such as zinc cadmium selenide. So solid state interfacial reactions depends on contact area, mass transport of reactants through product layer, nucleation and growth of product phase. This again can be systematically governed or monitored through a parabolic growth kinetics. Here is another example of cadmium sulphate zinc oxide which I mentioned, the metathesis. Here this is very interesting because both the reactants what we have and the product, they all have the same crystal structure, but the reaction that is proceeding is of a very intricate nature. We take the surface of cadmium sulphide and then we have zinc oxide, but what happens here is both cadmium has to go into zinc and zinc has to go into cadmium such a way that you have the anions exchange. In other words, in this case these are the anions. So you have the anion close packing that is intricate, but cadmium has to diffuse into the zinc site and zinc has to diffuse into the cadmium site. It looks very simple, but then it is a diffusion controlled mechanism where the cationic mobility dominates this conversion process. So this is a classic example of how diffusion control mechanism holds a very important role in the solid state synthesis. Here is another reaction where the metal exchange reaction is also achieved, and this can look very simple, but again this is very complicated. For example, you take copper and silver chloride giving copper chloride and silver, or copper treated with silver sulphide giving copper sulphide and silver metal. This is purely based on ion migration and electron exchange interface. So two things are happening, one is the ionic mobility is there and also there is a electronic mobility. So as much as the ionic mobility is happening between these two interfaces, now there is also electron mobility that is to be taken into consideration, because it has to happen that way for this new reaction products to be achieved. So this again looks very simple, but it is intrinsically a very complex process. Take for example another solid state reaction. Let us take a example of a solid with a liquid or a melt giving solid products. The best example here in this case is the Grignard reagent formation. Okay, take the case of magnesium metal which is a solid, and then you have Rx, that is alkyl halide, which is liquid, and then you also have ether which is a liquid. Now to form this solid product you actually have to go through several fundamental steps which looks simple, but it is very intricate. And another classic example of solid liquid melt is your hydrogen incorporation in lithium aluminum hydride, where lithium ion for hydrogen ion exchange between AlO2 layers are achieved, and this is also a very sensitive reaction, and basically these are controlled by surface defects, adsorption, dissociation and other diffusion mechanism. Just to show what are the various steps that happens in solid state synthesis, you take again the example of Grignard formation. In this case actually the alkyl halide actually gets absorbed in the initial reaction with the magnesium metal which is having a 0 valency. Now once bonds are formed, now this sort of species is formed, which now is taking another molecule of ether, and this is now getting detached from the magnesium metal surface. So many things happen, one is the RCl surface adsorption, and then oxidative addition that is happening, and then magnesium bond breaking occurs, and after that you have the ether getting coordinated to magnesium, and then the Grignard surface desorbs from the magnesium metal. So many things happen, but it looks as though it is a very easy process, but the solid state chemistry that is involved is really peculiar there. So when thinking about material synthesis, what is solid state materials chemistry all about? It is the synthesis and chemical and physical properties of solids with structures based upon infinite lattices or extended networks of interconnected atoms, ions, molecules, complexes or clusters in 1D, 2D and 3D. So it is a quite involved mechanism. Different techniques and concepts for synthesis, characterization and properties measurements of solid state materials, from those conventionally applied to molecular solids, liquids, liquid crystals, solutions and gases. So fundamentally this solid state approach is very different from what we usually encounter with the molecular solids, and we can therefore play around with a various class of solid state synthesis depending on the type of end products that we are looking for. So this brings us again to focus what sort of approach that we are using. The slides which I showed in the initial part of the lecture, again we come to the portfolio of solid state materials. So we need to go based on the reactivity of the solids, based on the functional application, based on the reactivity of the starting materials or the structure. We can play around with a host of preparative routes. Not only this, but thin film routes, nano approaches can be made in order to realize different sort of chemical compounds. In one sense we can briefly sum up to say that the factors influencing reactions of solids involves reaction conditions, temperature, pressure and atmosphere, structural considerations, reaction mechanism, surface area of precursors, defect concentration and defect types, nucleation of one phase within the other, diffusion rates of atoms, ions, molecules, clusters in solids, and then we can talk about the epitactic surface and topotactic bulk reactions with the lattice matching criteria to minimize elastic strain, and then surface structure and reactivity of different crystal planes. So many factors do affect the solid state synthesis, and especially to make new functional materials, all these issues have to be taken into consideration. Yeah, I will now take you to through some of the reactions which stands as archetype for solid state reactions. One of the classic example is the formation of magnesium Al2O3 or Al2O4, which is a spinel, and how this formation of this compound can be monitored. Now this can be kinetically monitored. Let us take the single crystals of MgO and Al2O3 when they are kept glued to each other's surface, and then one can monitor how the formation of this spinel can be achieved. The model reaction is MgO plus Al2O3 giving MgAl2O4, and this is a spinel which is a cubic close packed one made of oxygen close packing. Now here the beauty is magnesium has to go into 1/8 of the tetrahedral voids, and aluminum has to go into half of the octahedral voids selectively. Now all this has to happen when you just keep one crystal with the other crystal and you start heating it, and this is what happens. Magnesium has to travel from this interface, this region, into the interface along this direction, and Al3 plus has to travel in this direction. So as this diffusion is happening, then you will see progressively at the interface a product is forming, and this is initially the original interface at time t0, and once you start heating it you see this yellow patch that is forming, which is nothing but your spinal phase, and this yellow phase is the MgAl2O4 new product layer thickness, and this thickness is actually increasing with time in such a way that this will amount to, from this original layer, x by 4 times of this will propagate towards the MgO layer, and 3x by 4 times it will be propagating towards the Al2O3 layer. So the product front will actually travel in both the directions depending on the mobility and the concentration of aluminum and magnesium respectively. So if one magnesium has to go in this forward direction, then 2 aluminum has to travel in this direction. As a result, you will see the product front is actually growing much faster in the Al2O3 interface rather than the MgO interface. So this can be clearly monitored, and at time t we can try to see how much of this spinal phase has grown. So in this solid state reaction you can see this is thermodynamic and kinetic factors are at work, both are playing a vital role in the formation of this product. Yeah, the spinel is formed eventually because of the solid state precursors. So what are all the issues that are happening during this solid state reaction? Number 1 is thermodynamic and kinetic factors are to be understood, how they can limit this formation. Number 2, we should know the site occupancy, and therefore if you know the site occupancy, then we will also know whether the ionic size is suitable for such a solid state reaction to happen. and then we should also know the single crystal precursors, whether they are conducive, whether they are defect free, and the interfaces between the reactants and the temperature that is applied for this reaction to occur. On reaction, new reactant product that is MgO MgAl2O4 and Al2O3 MgAl2O4 interfaces form, and progressively, as you see here in this type of reaction, the free energy of spinel formation is always negative, and therefore it favors a reaction, and the high energy of activation means extremely slow reaction at normal temperatures, but you can see this reaction rate is enhancing if you are going to increase the temperature to 1500 degrees centigrade. Similarly, one can actually follow the reaction kinetics of MgFe2O4, which is spinel again, and this is popularly known as Kuykendall effect, because in one case MgO is a colorless solid and Fe2O3 is a brownish orange solid, and together it will give you a brown solid. And it is very easy, if you take a MgO crystal and Fe2O3 crystal and you try to keep that at the interface and start heating it, you will see different color interfaces happening at that point, and therefore you can easily monitor the kinetics of such a reaction, which is nothing but the Kuykendall effect. And there are other examples to such process, and we can calculate the Kuykendall ratio. For example, reaction involving strontium oxide and TiO2 gives you Sr TiO3, and we can take 2 Kf plus NiF2, which is K2NiF4 type of structure, and so on. So we can also try to monitor based on the colored interfaces. There are other examples to that end, easily monitored with colored product such interface. For example, nickel oxide, which is a green oxide, and Al2O3 is colorless, together it will form a faint green, they form a blue oxide, nickel Al2O4. Again, here in this case we can determine the reaction kinetics using Arrhenius plot, and we can try to monitor the energy of activation of this reaction. If you take for example 2 rock salts, for example this is the famous NaCl structure, MO rock salt crystal structure, this looks simple, but actually this is 2 penetrating FCC lattices, FCC lattice of oxygen with M in every octahedral site, and therefore they form a cubic array of corner and edge sharing octahedral building blocks. And if you actually look at this structure, it is very important to understand how this reactions proceed, because within this FCC lattice you will see 2 rock salt lattices mixed together. One is with the red core as your center, which is octahedrally coordinated, and second is this black sphere, which is octahedrally coordinated to 6 red spheres. So it can either be a MO6 octahedra or OM6 octahedra, and together they can form either a corner shared polyhedra or they can form a edge shared polyhedra. This is edge shared because the edges of this octahedra is actually in phase with 4 other octahedras. So to make either a corner shared octahedra or edge shared octahedra, solid state reaction has to be very selective. It cannot give mixed ones, but it is very selective dependent on the type of rock salt structure that you are using, what sort of the cations, that cation anion that you are looking for will determine whether you get a corner shared or a edge shared polyhedra. Again corundum structure is there. This is a octahedral block representation of Al2O3, which is having a corundum structure, where this is made out of a hexagonal close packing of oxygen, where 2/3 of the octahedral sites are occupied by Al2O3. So this is again a very selective site occupancy. So if any doping has to be happening, then it has to go into this selective sites of this octahedral sites where aluminum is doped, and that will determine the property of the substituted solids. Spinel crystal structure is another good representation of how the solid state reaction happens. This is another complicated crystal structure where the whole network of spinel structure is made out of oxygen close packing, where 1/8 of the tetrahedral voids is occupied by Mg2 plus and half of the octahedral voids are occupied by Al3 plus. So the trivalent metal ion occupies the octahedral site and the divalent metal ion occupies the tetrahedral site, and here again the diffusion or the solid state reaction is a time consuming process because each of these metal ions have to go and occupy the respective sites. It is not possible for the aluminum to occupy the tetrahedral sites, therefore the solid state reaction conditions has to be optimized such a way that effective occupancy of magnesium and aluminum in tetrahedral and octahedral voids is achieved respectively. And another very important structure in materials chemistry is rutile structure, where you have the metal ion which is actually coordinated to 4 other oxygens in this fashion, and they can be edge shared or they can be face shared or corner shared depending on the size of metal ion and the anion that you are looking for. The next important class of compounds which takes our attention in solid state synthesis is the perovskite crystal structure. This again comes from a MO6 octahedra, and this MO6 octahedra forms the corner shared polyhedral stuff. So doping selectively for the metal site is very important technique where solid state chemistry synthesis can play a very vital role, and therefore it is actually called as a perovskite chameleon because you can very easily modify the property of this perovskite by carefully doping either into the oxygen site or the metal site, and therefore defects and non-stoichiometry control the structure property and as a result the utility relations. There are classic examples of this perovskite compounds. One is lithium niobate, which is a nonlinear optical ferroelectric which is used in electro optical switch. As you can see here, the perovskite lattice can be still maintained with a pentavalent niobium and a monovalent lithium. Still they can stabilize a AbO3 type of structure, or this can be a divalent and a tetravalent cations, strontium titanium. These are dye-sensitized semiconductor used in solar cells, SrTiO3. Then we have HXWO3, which is a proton conductor, and this is used in hydrogen oxygen fuel cell as a electrolyte where you can carefully try to dope hydrogen in a WO3 matrix. And as I told you earlier, we also have other perovskites, for example this high Tc superconductor, and then barium titanium, which is a ferroelectric. We can use it for holography applications, and we have a lanthanum manganite doped with calcium. As I told you earlier, this is used for spin control of resistance and used in data storage. Lanthanum strontium manganite used in solid oxide fuel cell as cathodes because it is a good oxide ion conductor, and we can also make several perovskite compounds like PBS ZrTiO3, which is used for piezoelectric applications used in AFM and so on. So many different sort of compounds, and you can see a variety of cations that you can dope maintaining the same structure, but you can end up with a range of properties from magnetism to conductivity to ionic mobility. You can go for any sort of property, and the precise control of the size and shape of these materials will help in the utility applications. K2NaO4 is another group of structure which is important in the materials chemistry, where you can see this as a repeat layer of NiF2 Kf Kf NiF2 Kf Kf and so on. So you this is a special case of a perovskite that you can make, where you have this NiF2 sheets with intersheet of K plus, that is stabilizing this K2NaO4 structure. So in essence we are actually looking at few issues that are fundamental to the solid state synthesis. Size, shape and defects are everything, so to say. The morphology and physical size of the product controls synthetic method of choice, rate and extent of reaction and reactivity. Single crystal, phase pure, defect free solids, they do not exist, and if they did, not likely of much interest. Single crystals that has been defect modified with dopants which are intrinsic, extrinsic, and this can control the chemical and physical properties, the function and utility, and therefore when we look at all these combinations, we can single out to say that shape determines the solid state synthetic approach. So if you are looking for microcrystalline powder, then wherever single crystal cannot be used and it is not preferred for industrial production, you can resort to a powder form, and certain applications where large area useful for control of reactivity, catalytic chemistry, separation materials and energy materials can be achieved just with microcrystalline powder. Suppose you want polycrystalline shapes like pellet, tube, rod and wire, then we can go in for such chemical processes where we can get that for applications like superconducting ceramic wires, ceramic engines, magnets and so on. Then you can think of single crystal or polycrystalline film. If we are looking for use in microelectronics, in optical communication, photonic applications, we can go for epitaxial film. If we are looking for photonic and electronic applications, or we can go for glassy substances, fibers, films and so on for a range of optoelectronic applications and so on. So in all this we see that the role of chemical synthesis is actually based on the sort of utility that you are looking for. So based on that you need to modify your chemical applications. Lastly, I just want to finish with this beautiful figure. These are nothing but superconducting helical flexible nano cables, and these are actually formed by chemical synthetic routes. Size and shape and surface is everything in the solid state, and especially at this time it is more on the nanomaterials world. So with this I finish, and then we can look at several chemical approaches in the upcoming lectures.